All right, guys, welcome back. And this is going to be a video about 9.1, which is our first section in chapter 9. And chapter 9 is going to be all about this concept called confidence intervals. Now, let's give a little background before we talk about specifically what confidence intervals are. You see, in chapter 1, we introduce this definition of statistics. We collect data, we organize it, we analyze it, and we interpret it. We are entering into the analysis and the interpretation phase of our study of statistics. And one of the concepts we specifically were looking at in chapter 8 was this idea that while population data is nice and a lot of our formulas require population data, the reality is we don't always know population data. This is because we run out of time. We don't have enough money or resources, and it's simply a lot of effort to get population data. Think about me trying to calculate the average length of a trout in that pond, the population mean mu. It's impossible to get all the fish out of the pond and get the exact value for the population mean. So what we introduced in chapter 8 is instead of trying to find all the population data when that's unrealistic, values such as mu, sigma, all those things. Instead, we will take samples and calculate statistics to evaluate or predict the parameters. We're going to take sample data and use it to make predictions about the population. And we did this a lot in chapter 8. We took, if you don't remember, all those fish in the pond, we couldn't catch them all and find their average length. And so what we did instead is we took 100 samples, all of size 5, calculated the 100 sample means, and looked at that sampling distribution and used that to make predictions about the population. We discussed the concept that the mean of all the sample means would equal the population mean, and concepts such as that. And we're going to continue that theme of using statistics, sample data, to make predictions about the population here in chapter 9. So bringing back to our topic of conversation, confidence intervals, where do they fit into all of this? Well, the reality is, because I don't know population data, I'm going to have to use sample data to make predictions about that population data. But I want to be confident in my prediction. Thus, we're going to come up with these confidence intervals, which are intervals we are confident data will be in, which makes sense in a little bit. So let's first look at a definition. And it'll seem a little out of sorts, out of context, but as we go through the lesson, it'll make more sense. So our first definition: if a population distribution is symmetrical and mound-shaped, and the sample size is greater than or equal to 30, then we can assume that sigma equals S. And remember, sigma is our population standard deviation, and S is our sample standard deviation. Sample standard deviation. So what this definition says is if we know the population is roughly normal, symmetrical and mound-shaped, and our sample size is bigger than 30, then we can assume that the population standard deviation equals the sample standard deviation. Now, how's this different from what we've been discussing? Well, chapter 8, we looked at the distribution of sample means. So here's the analogy we could think of. If what this definition is saying is if I know all the fish in the pond have a roughly normal distribution, then I then take a sample, if I catch 30 fish, a sample of size 30, I catch 30 fish, and I find the standard deviation of those 30 fish, that will equal the population standard deviation. That's what this definition says. Chapter 8 was all about the distribution of sample means. Take 100 samples, calculate the mean of each, and then the standard deviation of those 100 sample means was the population standard deviation divided by the square root of the sample size. I want you to see the difference there. Here, I'm taking one sample of size 30 and finding the standard deviation. That will equal my population standard deviation given the specifications described in the definition, versus taking the standard deviation of 100 sample means. That's the population standard deviation divided by the square root of the sample size. I don't want you confused about why there's no divided by square root of n here. Okay, so definition number one, if a population has a rough normal look to it, and we take a sample of at least size 30, then our population standard deviation will equal our sample standard deviation. Well, great. If our population standard deviation equals our sample standard deviation when we take a sample, then we don't need to estimate it. And you're right. Here's the problem. What we're going to focus on 9.1 is estimating the population mean. And the problem is estimating mu is not as simple because unlike the population standard deviation and the sample standard deviation, the population standard deviation does not equal the sample mean, or the population mean does not equal the sample mean. While a roughly normal distribution with a sample size, if you take a sample size greater than 30, we could say the population standard deviation equals the sample standard deviation. Not the same case for the population mean and the sample mean. Well, if they're not the same, then there's obviously a difference between them. And we're going to call that difference the error of estimate. The error of estimate. Again, what we could imagine here is if I have a population mean of 10, a sample mean of 7, the error of estimate would be 3. Okay, the difference between that population mean, or the distance between the two, the population mean and the sample mean, is called the error of estimate. Okay, so we just find the error of estimate and called it a, well, not quite. See, again, the problem lies in that we don't know the population mean. We want to use the sample mean as a predictor, but we can't use the error of estimate just as a predictor because we don't know the population mean. So what are we going to do? Well, because we don't know the population mean, we are going to come up with an interval of numbers we think the population mean is between, as well as how accurate that interval is. This is called a confidence interval. We don't know a piece of population data, a parameter, the population mean. So we're going to predict it with the statistic that corresponds to it, the sample mean, by using that sample mean to come up with some interval of numbers we think the population mean is between. I may not be able to tell you what the population mean is for all those trout in the pond, but I at least want to be able to come up with an interval of numbers that I can say with a degree of certainty, hey, I don't know the mean of all the fish in the pond, but I can tell you it's between blank and blank with this amount of confidence. That's the idea that we're going to kind of go after here. And really there are two parts to this. Number one, we want to come up with the interval. The average fish in the pond is between blank and blank. And we need to come up with how accurate it is. I'm 60% confident that the number or the average length of a fish in the pond is between 10 and 12, since I can't say it's 11.5 for certain. So we need to figure out the accuracy of our interval and what the interval is. So let's focus on the accuracy side of things. How are we going to come up with an interval that we know is accurate? Well, what we're going to do is we're going to look more closely at the standard normal curve. And remember, the area under the standard normal curve equals probability. Specifically, we said if I had a standard normal curve here, and we said 95% of my data, have a standard normal curve here, mean 0, standard deviation of 1. The empirical rule told us that 95% of our data was between 2 standard deviations below and 2 standard deviations above on a normal curve, which means for the standard normal curve, I can say that 95% of the data, according to my empirical rule, falls between -2 and 2 on the standard normal curve. Again, that's because it has a mean of 0 and a standard deviation of 1. But I can flip that statement around and say instead of that 95% of the data falls between -2 and 2 on the standard normal curve, since area under the normal curve equals probability, I could say I am 95% confident that a random value on the standard normal curve, I am 95% confident that a random variable, remember Z is the term we use when we're working with a standard normal curve, I'm 95% confident that a random variable Z on the standard normal curve is between -2 and 2. Because we know the area under the standard normal curve is probability, we are going to use it to evaluate the reliability of our confidence intervals. So if I want a 90% confidence interval, I need to find the 2 values under the standard normal curve that 90% of the data lies between. I used the example with 95% above because by the empirical rule, we know it's -2 and 2. But you can do this for any amount of area or whatever level of confidence you want. The values that such amount of data is going to be between is called the critical values. So in the example I gave above, -2 and 2 would be the critical values. So first things first, before we get into, I know this is probably a little confusing right now, before we get into the big picture of actually finding a confidence interval, let's look at a couple examples and find critical values for different amounts of confidence. Let's say that I want to be 99% confident in an estimate between 2 values. Part of me finding the confidence interval means I need to find 2 critical values. We'll give them the label -Z of C and Z of C. Remember, Z represents a random variable on the standard normal curve, C standing for critical value, such that 99% of the area under the standard normal curve is between them. If we want to be 99% confident, we're going to look at the standard normal curve and say, okay, here's 99% of the data. 99% of the data. Let's find the 2 values such that let's find these 2 values such that 99% of the data is between them. Because again, area under the standard normal curve is probability. So if I find the 2 values such that 99% of the data is between them on the standard normal curve, then I can say I'm 99% confident that my random variable Z will fall between those 2 values. So how do we find 2 values on a normal curve when we're given a probability? Well, that's a chapter 7 question. Inverse norm. I need to find these 2 values. And I am working with the standard normal curve, so I can use inverse norm. So if I want to find two values so that 99% of the data is between them, then what I'm going to need to do is I need to identify that 1% of the data is outside of this shaded region, which means 0.5% is in each tail. And so for my inverse norm setup, remember I need to identify the area left of each value. Turn your percents into decimals. And when you solve this, you get negative 2.58. 2.58. For my right value on my standard normal curve I'm trying to find, 99.5% of the data lies to the left of that. So I plug in 0.995 as my area left, 0, 1, and I get 2.58 as my right value. So looking at my answer in the context of the problem, I want to be 99% confident that an estimate I'm trying to make lies between two values. Well, I need to start that process if I want to be 99% confident by looking at the standard normal curve and going, what are the two values that hold 99% of the data between them? Because then I'm going to be 99% confident that a random variable z on my standard normal curve is between those two values. Let's do another example. What if I want to be 90% confident in my confidence interval that I'm going to find? Well, I'm going to start that process by finding two critical values, negative z of c and z of c, on the standard normal curve such that 90% of the data is between them. Again, for the millionth time, that's because the area under the standard normal curve is probability. So if I find the two values that have 90% of the data between them, then I can be 90% confident that a random variable z on that standard normal curve I can be 99 or 90% confident that a random variable z on that standard normal curve will be between those two values. So I've got 90% of my data between these two values, and I'm trying to find the two values. How do I find values on a normal curve when I'm given an area? Inverse norm. Well, with inverse norm, we know we need area left. We already have the mean and standard deviation because we're working with the standard normal curve. So, what is the area left of negative z of c? Well, if 90% of the data is between negative z of c and z of c, then 10% is left over outside of the area between those two values. 5% on each side. So what's the area left of negative z of c? 0.05. What's the area to the right of z of c? 0.95. When you run these calculations, you get negative 1.645, which would be your left critical value, negative z of c, and 1.645, your right critical value, z of c. Again, interpreting our answer here, I want to be 90% confident that my estimate lies between two values. Well, when I'm looking at the standard normal curve, that means my two critical values are going to be negative 1.645 and 1.645 because 90% of the data lies between those two values, meaning there's a 90% chance that a random variable on that standard normal curve will fall between those two numbers. Guys, thanks for watching this intro to 9.1. We'll get into the more practical side of things in the second part of the video.